with the capital charge under SBM or the sensitivity based method. Now, as we know, the SBM capital charge talks about linear and non-linear risk charges. Now, these can be studied in two buckets. So, the linear risk charge will study the delta risk and vega risk, and the non-linear risk will be a study of curvature risk. So, starting with the delta risk. So, this captures the change in the price of an instrument for a small unit change in the underlying risk factor, maybe an interest rate, stock price, etc. So, a common example of this could be, let's say, a bond duration, for example. Now, we know bond duration is nothing but the sensitivity of the bond price to the change in yield, right? Because we know that bond price is a function of yields. Take a simple government security, for example. So, duration is defined as the rate of change, or maybe it's defined as how the bond price is going to change for a given change in yield, isn't it? And duration is also like a linear measure, which we commonly study as a part of fixed income mathematics or in bond pricing. So one could visualize the definition of delta from so for example, we can relate that with the duration point of view because it's conveying something similar. So for a small change in yield, we try to understand what is the change in price. So that is exactly what this definition says as well. Now, this is a risk measure that is based on the sensitivity of the trading book to the regulatory delta risk factors. Then we have the vega risk. So vega risk captures the change in the value for an option resulting from the change in volatility of the underlying risk factors. So as the underlying risk factors fluctuate, this is going to have an impact on the value of the instrument. So this is the risk that is based on the sensitivity of the trading book to the regulatory vega risk factors. So delta and the vega risk are composed or they are bucketed under the idea of linear risk. We have a non-linear risk as well, whereby we study the idea of curvature risk. Now, this is going to capture the incremental risk which is not captured by delta. So, for example, let's say I look at the change in the price of an option, for example, something like this. So, take an example of a call option, just for example's sake. Now, if I look at a certain point, let's say I'm at this point, let me just switch inks. So if I'm at this blue colored point and I wish to understand the sensitivity at this particular point, then I could define it via a straight line, isn't it? So we could define a straight line measure and it could help us understand the delta risk because as we know, delta risk is a linear risk. And a linear risk is something which can be represented or explained via a straight line measure, as we are shown as this line in blue. However, if you have to understand the total risk which is embedded in this call option, there is also this curvature bit which will need to be studied, isn't it? Because if we ignore this curvature bit, that implies that we are ignoring that component of risk. So then we are not capturing the entire risk which is there. So in order to go a step ahead and to capture the risk which the straight line fit or the delta risk is unable to capture, we require a curvature risk. So as it says, if the price of the option moves more than the delta when the price of the underlying changes, then the curvature risk is calculated by a certain way, which FRTB says. So it says you can calculate this by taking a difference between the price change explained by the delta risk from the total price change. So the easy way to do that is to compute how much is the impact impact in the price change which is given by or explained by the delta risk, and you compare that with the overall or total change in the price which has happened, and we simply take a subtraction. So you can imagine it's like that residual component, isn't it? So we have this curvature risk which could be explained in simple arithmetic terms as the total price change minus the price change explained by delta or delta risk. So this is what we call as the curvature risk. Now this risk is based on two scenarios. So we take two conditions. One is what we call as an upward shock and a downward shock which we apply to a given risk factor. So that given risk factor could be, let's say, the underlying stock price, for example. Let's say it's a call option on a stock. Then my underlying risk factor becomes the stock price. So we apply an upward and a downward shock on the underlying stock price. And from this, we pick the worst case loss of the two scenarios, and this is used for calculation of the capital charge. Now, one point to note is that the Vega charge and the curvature charge is applicable for only option and option-like products. So when you say option-like products, you can think of certain products which have properties of an embedded option. So Vega and curvature charge apply for option and option-like or the embedded option products.